And we need to obviously do something in order to try and improve our overall designs. So the first way we're going to look at that is we're going to be trying to calculate our total heat gains. And obviously, the first thing that we need to do is know what is the square footages of all of our materials outside for our total building envelope. You know, how much window area we have, how much wall area, how much roof area. Ideally, how much perimeter of the floor we have, but we're not going quite that far at this preliminary stage. We'll worry about that next year, or next semester, I should say. So the good thing is, we actually have a table here of exactly what it is that we're looking for. We're looking for the U values of all of our different materials. As well as all of our square footages. Now for me, I already have, at the very least, these square footages listed out. So for this particular example, these are the square footages that we're going to use. Let me see if I can zoom in for you guys just a little bit. Everybody able to see that pretty good?
Are those values your gross or net square footages?
Those are net. I should say net for everything except for the obvious, for the floor area. The floor area itself is gross.
Do you recommend rounding to the tens or to the hundreds?
In this case, you would just round to the nearest square foot.
Okay.
Realistically, I mean, if you want to get, really, really specific, 1 square foot difference isn't going to make that much of an impact. We're talking about tenths to hundredths of a % of the overall square footage that gets adjusted. And for the actual computer programs that you use to ultimately prove that your building meets code compliance, they round to the nearest square foot. They don't even go to the tenths. So realistically, the nearest square foot is about the furthest you need to go. But for U value, when you do the U value, I would go all the way out to the thousands. Again, most computer programs will actually go off that far, and that's how far they end up running. Everybody got this down? All right. Now I know it's a little bit of a pain in the ass, but we got to write it down in another spot. And I don't have that one filled out, so I'm going to start writing that out right here. We're going to fill out the overall area of the entire envelope for the north, west, and east for our heat gains. So that's a combination of the glazing area as well as the opaque or net wall area. So this would be just the opaque surface. And then obviously we have our glass. So let's fill that out. Let's see, for the north I got 800, south I don't have to worry about, east 370, west 480, glazing. So our overall gross area is the combination of both of these. So the opaque wall area plus the glazing area. So we've got 1,100 square feet. We've got 600 square feet. We've got 450. And again, these are all going to be what your actual building is. So this is my particular building. I'm just going through the steps to kind of show you how to actually do this. So obviously, adjust these to meet what your design is. Okay? All right, so we got all this listed out. Our roof area, I have that as 1,800 square feet. And for my particular building, my building is only 1,700 square feet. Now, why would my roof be more than my floor area? No, we don't have to worry about overhangs because there's not conditioned space over those overhangs. It's because it's sloped. If you have a sloped roof, you're going to have greater surface area. So if it's a flat roof, you can pretty much just say they're exactly the same. The difference is going to be, that 1 or 2 square feet because yes, you do still have to slope it just a little bit. So yes, there technically is more square footage, but you can argue that it's exactly the same. Yes?
For our house project, are we assuming it has a traditional slope roof?
That's up to
We
you.
need a flat roof.
That's up for you to decide. You're the designer.
But if it has no overhangs.
If you have any overhangs, again, all we are going for is all the way to conditioned space. So if your wall is here, if your roof overhangs, you're only going to take it all the way to the actual wall.
I mean, if it's flat.
Even if it's flat, go all the way to the edge of the wall. So yes, even though technically you're going to have it where there's a parapet and everything, I would still consider that little spot as part of your roof. Because by all means, we're still going to have energy coming through at that exact corner. So realistically, your roof, even though there is a parapet wall that's over it, that helps shade it and block it, it still goes all the way out to the very edge. For your exterior, if you're looking at your elevation, if you've got that flat roof, you do not have to include any of the actual parapet area. It's only to where you actually have conditioned space. Make sense? Questions? No good? All right. So now that we have all of this listed out, we need to add up the totals. So we're going to add up the totals for the overall gross envelope area, our glazing area, and our opaque or just net wall area. So if we add all of this together, we get 2150. We have a total of 500 square feet of glazing that is not south. And we get 1,650 square feet of opaque wall that is not south. For my roof, if you have any skylights or anything that's obviously up there, they'll list out what your glazing areas for your roof. I don't have any, so I'm just going to leave that blank, which means I still only have 1,800 square feet of opaque area. Now I need to figure out what is my overall opaque non-south skin area. This would be for the walls. So this is for walls. We also need to figure out what our percentage is for roof. And what our percentage overall is for our glazing. Again, we're just looking at everything that is not south. So in this case, we're going to take our wall area, and we're going to divide it by the total, which in this case, we've got our total wall area here, plus our roof, gives us our total non-south envelope. If we add the two of these together, 2150 plus 1800 equals 3950 square feet of total non-south area. 1650 of our wall divided by our total non-south area will give us our percentage here. Our overall window area divided by our total square footage gives us our window percentage. And then our roof divided by our total area gives us our roof percentage. So 1650 divided by 3950, that's going to give me 41.8%, 0.418, we're going to convert that to percent. 2,500 divided by 3,950 gives me 12.7%. And then 1,800 divided by 3,950 gives me 45.6%. Now, if you add these up, ideally they equal 100%. In my case, they don't. They equal 100.1%. Again, that's okay. That's just a rounding error. Because we rounded all three of these individually, we can add them up. We might be off by 0.1%, either positive or negative. So as long as you're 100.1 to 99.9, if you want to adjust any of these and say, I'm adjusting it to correct for that rounding error, by all means you can. That's a good justification. If you want to leave it as is and say, hey, it's just a rounding error, it's not going to mean that much, again, that's also good justification. Either way is fine with me. Our total non-south opaque envelope area, which is your total net plus your total net roof area, is just kind of giving you what your overall opaque area is. It's not going to really mean that much. If you want to know what it is, by all means, you can fill this out. If not, you can leave it completely blank. It's not really going to help us with our overall calculation here. It's just for additional information should you actually choose to use it. So in this case, we can actually add our total opaque areas here and get what our actual overall opaque envelope is. So it's up to you if you want to leave that blank. It's not going to mean anything. So this one is not needed. Any questions so far? Yes?
Why is that not needed?
Because we're already breaking out the percentages individually between the walls and the roof. If we had the exact same U value or R value for both the walls and the roof, then we could actually just go ahead and combine them and say, hey, they're realistically the same material, but because we're actually breaking them out, it's not needed. Anything else so far? All right, now we've got the total exposed skin area divided by your floor area. So that's going to be our total skin area divided by our overall floor area. So 3,950 divided by 1,700 gives us a factor. In this case, our factor is 2.32. Now, with our overall percentage of windows, plus our factor of total envelope over our floor area, and our overall U value that we will eventually calculate, that will help determine how much heat flow we have coming through the actual building's envelope, at least for everything that is not facing south. And again, this is all taking into consideration worst case scenario, where that south facade has gained all of that solar radiation throughout the day, that all of the heat that it's losing is just everything that it's storing itself. Does that make sense? That's the entire reason why we're not considering south in these calculations, is because it's not necessarily gaining or losing any heat that's inside the building. So next we need to know what's our R value for our roof and our walls. Our window, we're actually going to factor it as part of our percent of the windows and whether or not it's single pane, double pane, or triple pane. So all we need to know is what's our R value for our roof, what's our R value for our wall. And with that, we can look at what is recommended for our particular climate. This right here is the ASHRAE climate zones. And this is the particular map. If you're actually doing any sort of LEED projects, these are the climate zones that LEED follows. They just follow the ASHRAE standard. If you look, we're designing for Las Vegas, which is a 3B climate. So our climate zone is a climate zone 3. The reason it's B is because we're in a, well, dry and arid climate. That's pretty much the only difference between A and B, whether you're in moist, dry, or marine. So if you're in California, primarily. So 3B, we're in climate zone 3. We're looking for roofs, and for my particular roof, I'm going to have a wood roof with an attic in it. So I'm recommended to have a 16-inch total envelope roof. So that's all of my membranes, the actual sheathing, the actual framing, the insulation, everything that's part of the actual roof. It's going to probably be around 16 inches. And they're recommending that it should be between 30 and 60 for my R value. Recommended is at least 50. So I'm going to say that I'm going to recommend at least 50.
What's the margin of error for that 16 inch? Like, do they come in and measure it?
They don't come in and measurement. It all depends on what kind of materials you're using, what kind of insulation you're using. I mean, this right here, again, is for very, very preliminary design. So 16 inches is probably on the very, very high end. Realistically, it's probably going to be somewhere around like 12 inches, 10 inches, again, depending on the type of insulation that you're going to use.
So, so one can decide just going off of like nominal numbers at 2x4, go like with those dimensions, and it'll be less?
It'll end up being less, yes. Again, this is taking into account if you do like rigid insulation on top of it, plus your sheathing, plus the membrane, it takes into account all of that. So this right here is probably a really, really, really high number. And for preliminary designs, the higher the number as far as thicknesses, the better we're at when we come to design. Because we can always make stuff smaller, and people will be incredibly happy. It's where we start making stuff bigger and we start taking away square footages from different rooms or different heights or anything like that that's actually occupiable by people, where people start getting pissed. So the greater our numbers are for preliminary design, the better. So I'm going to say I'm going to go with recommended R50 minimum. So recommended for my roof is an R50. For walls, I'm going to go with still standard construction. It's a tract home, so I'm going to say it's a wood framed wall. They recommend somewhere between 15 and 21. It's not unheard of to do R19 insulation, where your overall building assembly for your wall is approximately around an R20 to an R21 for standard wood frame construction. So I'm going to go on the high end. I'm going to say my recommended is at least an R21. So recommended is an R21. Now we need to list out what our actual R value is. So again, this depends on what it is that you guys are designing. Realistically, we need to meet what is recommended. And if you go below what is recommended, you better have some justification as to why. Why am I going less than an R50? Why am I going less than an R21? You need to explain that. Okay? Again, realistically, we should be higher than these. This should be the absolute minimum that is recommended. So let's say for my particular design, I'm going to go with an R60 for my roof. And let's say I'm going to go with an R25. Again, your guys is going to be different. We want you guys to explain how you came up with your R values. So, explain this. Yes?
So you get those numbers just by adding up the materials that you just said?
You can do it that way. If you had a standard construction, you can easily use the tables that actually have that standard construction listed and they'll have the same information already calculated for you. Our R value is just the reciprocal of the U value is the reciprocal of our R value. So in this case, we got 1/60, which is 0.1 or 0.0167 or 0.017 if you want to round to just that hundredths place. That's up to you guys to decide. I'm going to go that one further just so I can show you it's 6 repeated. Our other U value, 1/25, 0.04. Again, always make sure you add your trailing zeros. Now we just simply add up our U values, correct? That'll give us our total building envelope. No. Similar to how it is that we calculate for our walls, we need to figure out what percent of our envelope is our roof and what percent is part of our walls. And we've already done that. We've got our percentages right here. So all we're going to do is take our percent for our walls, multiply it by our U factor for our walls. We're going to take the percent of our roof and multiply it by the U factor of our roof. So 41.8% times 0.04. Remember, this is a percent, so it's 0.418 times 0.04, which gives us a value of 0.0167. Again, you can round to the thousandths place. And for our roof, we've got 0.0076, 0.456 times 0.0167. Now we can add these two together. Add these two together, and that gives us our overall U factor for our opaque skin. In that case, it is 0.2432. And if you straight up add this up, I know it ends up being like 3.3 instead. What I ended up doing is I took this times this and straight up added them together. So I figured out what the overall percentage is all the way out to, the millionths place all the way out here, and rounded it up afterwards. So in this case, it could be, 0.2433, 2432. Again, it's not going to make that much of a difference, especially when we're trying to calculate that based off of our graph. If we look at our graph, I'm sorry, that should actually be 0.02. I apologize for that. 0.0243. That's my fault. I forgot a zero. So if we look at our graph, how are we going to calculate, the difference of 1/1000th? It's going to be ridiculously hard, and it's not going to make that much of a difference. Okay? Questions so far? All right, so now for figuring out our glass. Again, it all depends on what kind of glass you're using. If you're going to use single pane glass, so single glass, you're going to take this percentage and you're going to multiply it by 2. Don't worry about adjusting any other percentage. Realistically, the U value for single pane glass is twice that of double pane glass. So by multiplying the percentage by 2, that essentially compensates for that additional heat loss that's going through those windows. If you've got triple pane glass, you're going to divide by 2. And if you have double pane glass, just keep it the same. This is already for double pane glass. So in this case, if I've got single pane glass, I'm looking at a factor of, what are they doing up there? I have no clue. So in this case, I would have a factor of 25.4. If I were to take that in half, I would have it be down to 6.35. Make sense? All right. I'm going to go ahead and stick with the double pane glass. And now I have all of my information to figure out what my overall skin heat flow is going to be. And that is with this graph right here. We're going to start off with our U value of our opaque skin. That would be 0.02432, which is going to be pretty close to around 0.025. So right here is 0.1, 0.05, so I'm halfway between these two lines. I know it's really, really close down here. Obviously, if we had a computer, we can actually get a lot more accurate. So I'm going to draw a line straight up. We then take our percentage of double glazing. In this case, 12.7, which would be somewhere right here. And we're going to draw a line all the way to our right. Now, if we go all the way to the right, that tells us what our overall U value is, including our glass. So in this case, our overall U value is somewhere around 0.085 to 0.09. Obviously, with the amount of glass that I have, that made a drastic difference between that 0.02, now I'm all the way up to 0.09. That's a big difference. That's a big jump. I don't know if I've got too much glass. I probably do. But, oh well. Let's continue and see what the hell happens. Yes?
Is that 0.9 or 0.
Well, right here's 0.1.
Oh, yeah, sorry.
0.09.
What happens if you're not using double glazing with this chart?
If you're not using double glazing, this is where you would either double the percentage or half the percentage. So if you're using single glazing, we would be all the way up to 25. If we're using triple pane, we're going to be somewhere down in here. Okay? Next, we can figure out, okay, what was our exposed skin to floor area? What was that factor that we figured out? Which is this factor right here. So 2.32. 2.32 is somewhere in between 2 and 2.5. And right where this point intersects, if I draw a line straight down, that'll tell me what my skin heat flow is going to be. So right at about 0.2. Plus or minus. Which again, for preliminary, plus or minus is okay. So our skin heat flow is 0.2. Next, I need to figure out what's my infiltration or ventilation going to be. And it all depends on what kind of building I'm doing. Now, obviously, for the purposes of this exercise, we're only going to be using one of these tables. I wanted to give you all of the tables just in case you come across a different scenario where you're not doing just a residence. We've got the ventilation in commercial and multifamily buildings. We've got the actual fresh outdoor air required for ventilation, which we use to help calculate how much heat flow is coming through our ventilation. But we're designing a single-family residence, so neither of these really apply. We're going to be looking at what's down here for our infiltration and ventilation in residential buildings. So again, if you come across different scenarios, we have the information in this particular exercise. It's just not pertinent to you guys completing this exercise. Make sense? All right. Now notice we've got two different columns here. We've got one for imperial units and one for standard metric units. Obviously, we can ignore this because, well, we're not in Europe. And again, we're trying to design for worst case scenario. So realistically, we want to try and choose whichever type of situation we can realistically justify our building being in. So let's say I'm designing a typical tract home where I know the contractor or whoever's building this is not going to be that competent. He's just trying to build incredibly fast, turn a quick profit, and leave. Which, again, that's most of our buildings here in Las Vegas. So I'm going to say that I'm just doing a conventional insulated frame construction. Maybe I have it because of the new codes, they actually have to do a vapor barrier around the entire building. Which, surprise, surprise, a lot of them don't like doing. But it's going to be required with the new 2018 codes that we recently adopted. So I'm going to say I've got that vapor barrier. And worst case scenario means I've got a lot of wind coming through. So I'm going to say that my infiltration is a 0.18. So we input that here, 0.18. We add the two of these together. That gives me my total heat loss. So 0.38. Multiplied by 24 hours in a day. 0.38 times 24. I seem to be missing my hot sheet now. That actually had that answer. There it is. 9.12. This is where we can actually start comparing our buildings to other buildings that are not necessarily located in our climate. All we need to know is what are the overall heating degree days for Las Vegas. Las Vegas on average has 2,407 heating degree days. We're on 2,400. So that means we fall within the 1,000 to 3,000 category, which means for a conventional building, I should be somewhere around 8. And if I have some form of passive solar building, I should be around 6.6. So I should be somewhere between 8 and 6.6. I'm at 9.12. It's probably not a good thing. I need to do something. Especially if I'm going to move forward and try and put in a lot of passive designs into my building. Because where it stands right now, I've got so much heat loss that no matter what strategies I put in, all of the heat gains that I would get during the winter are immediately just going out of the building. So it's not really benefiting me all that well. Question?
Can you re-explain this last portion? Where'd you get the 2400?
The 24 what?
The 2400 on the bottom right?
So this right here is based off of our climate data. So if you look at the Las Vegas meteorological data, where they take the average temperature for the entire year, remember, a heating degree day is the different temperature between outside and inside, where it is colder than, and the typical heating degree day is 65 degrees interior temperature. So whenever it's 1 degree less outside, that's 1 heating degree day. If the average temperature is 5 or 10 or 20 degrees difference outside, that's 5, 10, 20 heating degree days for that one day. We're going to add that for all of Las Vegas for the entire year. And the average for Las Vegas is right at around 2,400. So this right here is just some meteorological data. So again, I need to do something. I need to bring this down. How can I bring that down?
Add insulation.
Add insulation, I can easily do that. What else?
Reduce glass.
Do what?
Reduce glass.
Reduce my glass, absolutely. Anything else? Better sealing, absolutely. Those are pretty much the 3 things that we can possibly do to make it to where our building is actually going to perform better. We need to do everything we can to make it to where these 2 numbers are as low as we possibly can. This number is all dictated on exactly how much insulation we have and how much glass we have. Obviously, if we want to, we can also adjust, okay, how much actual exposed envelope area there is compared to our overall floor plan. At this point, we probably already have our plan designed, so we're not going to really want to change a lot of that. So that could be a possibility. I don't know how well that would work. How far you are along in your design stage is going to help dictate that. So pretty much our insulation, our glass, and how well our building is sealed are going to be the 3 things that we can easily do to help bring this down. But again, remember, the more insulation or the more higher sealant we have to help completely seal that building, the more it's going to cost. And the more that your contractor is going to bitch at you. It's bound to happen. I've been yelled at by a contractor. Trust me. It's all going to be okay. So that right there is how we figure out, okay, how much heat loss we're going to have in our building. Again, the lower that number is, the better our building performs. So we want to make it to where that number is as low as we possibly can. And we want to be able to justify how we got that low number. Okay? Now we need to figure out how much are we actually going to get through our cooling loads, or how much we're going to have in overall heat gains. So heat losses is part of our heating load. Heat gains are part of our cooling load. And our cooling load is just a combination of everything for our envelope, the amount of heat gains we get from our people, from our equipment, from lighting, and from infiltration or ventilation. It's just a combination of all of these. That's all we have to do. For our envelope, we're just going to look at our windows, our walls, and our roof. So right here are the 3 points for our envelope. Now, for us to do our envelope, we need to know what's our outdoor design temperature. For Las Vegas, that is 103.4 degrees. Again, this is based off of meteorological data. You can actually get that number based off of need. So 103.4 is what we need to design for. That would be our average highest temperature that we can actually control. Now, yes, there are temperatures where it gets higher than 103. I get it. But again, that's only typically for an hour maybe 2 every day, and is it honestly worth adding another, 5 inches of insulation for 2 hours worth of actual cooling, when we're only talking about that for 1 month out of the year? That's up for you guys to kind of argue. I'm going with that ain't worth it, and no one's going to want to pay for it. So 103.4 degrees. How do I choose 103.4 degrees when my only choices are 90 and 100? Well, we can choose whichever one's closest. That's obviously an easily justifiable solution. Huh? 90 degrees? 90 degrees is closest to 103? All right. The other option that we can do is what's known as interpolation. I just sent you guys a little worksheet to kind of go through interpolation. I don't have time to go through it myself. I will tell you this right now for the quizzes. You don't have to worry about interpolation. Don't worry about it for the quizzes. Okay? I'm not going to be that cruel to you guys. If you want to do it for the exercises, by all means do it. Okay? I'm going to be lazy, and I'm going to say I'm just going to choose whatever's closest. I'm going to go with 100 degrees Fahrenheit. Which means here are my factors that I use for windows, for walls, and for roofs. So I multiply everything by 21, by 25, and by 45. So for my windows, all I need is my overall window area divided by my floor area times 21. Now this is all of your windows, including south. In this particular instance, we include our south area because we're looking at worst case scenario. The south is going to be gaining you a lot of heat gains. So include south. In this case, my window area total, let me pull that up real quick. Well, we've got 1,000 square feet of total windows. And we're going to divide that by our floor area, 1,700 square feet. 1,000 divided by 1,700 times 21 gives me 12.35. 12.35 BTUs every single hour for every square foot within my building. Just in my windows. So yes, I have an absolute shitload of windows, and I need to get rid of a lot of them. This is way too over-designed. Now I'm going to go for my opaque walls. We're going to take our opaque wall area, multiply it by our U value of the wall, and divide that by our floor area. So my opaque wall area total is 2,350 times 1 over 25. That's my U value, 0.04. We're going to divide that by 1,700 and then multiply by 25. Just follow it out. 2,350 times 1 over 25, 0.04, divided by 1,700 times 25. That gives me 1.38. For my roof, it's the exact same steps except for the roof. Our overall roof area times our U value for the roof divided by our floor area. So we've got 1,800 square feet times 1 over 60, or 0.0167, divided by 1,700 times 45, which gives us a value of 0.79. We add all 3 of these together, and that gives me all of my heat losses, or heat gains, sorry, all of my heat gains for my total envelope. If we add all that together, I get 14.52. Questions on that?
You said it was all the heat losses or gains?
Gains. So this would be heat gains, so total heat gains. Now, if we wanted to, we can go ahead and figure out our infiltration from the exact same strategy. So let's go ahead and knock that out since we're already on this page. So we've got infiltration or ventilation. Remember, if you're under about 2,500 square feet or doing single-family residential, your main focus is going to be for infiltration. All of those cracks and crevices that are part of your building envelope where air is pushing its way through. If it's over 2,500 square feet or larger commercial space, then you're going to be worried about ventilation, mainly. So I'm going to focus all my attention on infiltration, because I'm doing single-family residential. Again, we're going to design for the same temperature, which means I'm going to multiply by 27. Now notice we have two different lines here. One of them is for imperial, one of them is for metric, so we don't need to worry about the one on the bottom. And I know that it says infiltration load from technique 17. Before they switched over to Sunwind Light version 3, in version 2 it was called techniques, not strategies, and it's actually not even number 17 anymore. It is Sunwind and Light number A23. So whatever you got from A23 times 27. And A23, we've already figured that out. That was our 0.18. So it's the exact same thing that we did here for our infiltration. So 0.18 times 27 gives us a value of 4.86. Now all we need to do is figure out what's our people, our equipment, and our lighting. And all of that is located on the next page. Right here is going to give us all of our heat gains from people, all of our heat gains from equipment, and then over here is all of our heat gains for lighting. So let's look at people, let's look at equipment, and we're designing a residence. I'm going to say I'm just designing just straight up residential. So that means for people, I'm going to have 1 to 2 BTUs for my people. For my equipment, I'm going to have 1 to 2 BTUs per square foot for any sort of equipment that's inside. So that's going to include computers, televisions, stereos, cell phones, anything that's actually going to use electricity other than lights. Now, this gives you a range. You guys get to justify what number you choose. I'm going to say, I don't know who's going to live here. I'm going to sell this at some point because I'm a contractor and want to make quick money. So I'm going to design for whatever the hell anybody wants to put in there. So I'm going to design worst case. So I'm going to go with whatever's the highest. So I'm going to go for 2 BTUs for people and 2 BTUs for equipment. That way, if there's a lot of people in there, great, I'm still covered. If they have, servers that are in there, great, I'm still covered. If I go on the low end, then that's telling me that, oh, there's not going to be that many people, or they're going to have very, very light loads on the equipment itself. Does that make sense? All right. Now, we just need to know, in order to figure out how much we have for lighting, is what is our daylight factor. And we've already figured that out with exercise 2. We figured out what our daylight factors are for our entire building. Now, I know what some of you are probably thinking. Well, each room has a different daylight factor. So how do I actually figure this out for, an overall building? Do I just, do I have to break it out by, okay, how much percent is this daylight factor? How much percent is this daylight factor? Do I have to add all that up and take all of that time? Well, yeah, that's one way you can do it. Or we can actually use the calculated method, which is only your window area divided by floor area times 0.2. Yes,
Does this include south windows?
that includes south windows, so this is the entire building.
That's for daylight factor?
That would be for your daylight factor, yes. If you wanted to express it as a percent, then multiply by 100%. Otherwise, we can have it where it's just, decimals. Either way will give us a daylight factor. I've already calculated this out. Let me see what my daylight factor was. My daylight factor is 11.7%. Holy shit. Yeah, I've got a lot of glass. I should probably tone that back a lot by taking out 2/3 of it. That might help out everything that I'm designing. But let's say I'm not, I'm crazy. I'm going to stay with 11.7%, which means my daylight factor is definitely a lot bigger than 5%. I'm also designing for residential. And Las Vegas is located at 36 degrees latitude. Again, if you guys want to interpolate, by all means you can. I'm going to go ahead and say that I'm going to take whatever's the highest number that's between 30 and 40 degrees latitude. That way I'm covered for worst case scenario. So in this case, I'm going to say that I'm going to have a large amount of lights, so I'm going to go on the high end. Low end would be if you're doing, LEDs and you're energy efficient and you're trying to minimize how much lights there are. That's what that means. So I'm going to say I'm just going to have a lot of lights, and they're all going to be, incandescent light bulbs that no one ever makes anymore. Maybe they stockpile them. I don't know. So I need to choose somewhere between 1.1 and 1.6 BTUs per square foot. Again, I'll go worst case and say I'm going to go 1.6. Now to figure out my overall heat gains, I add all these together. That tells me how much I'm going to have for every single hour for every single square foot. Plain and simple. Add it all together, I've got 24.98 BTUs per square foot. If I were to multiply that by my overall square footage, that means I'm going to have about 42,466 BTUs. 42.5. That is ridiculous for a 1,700 square foot building. Realistically, for today's age, you should probably be around 15 BTUs per square foot. Realistically. So obviously, I'm a horrible designer and I need to be shot. But hey, again, this is a learning experience. I know that this is a little too high. I know that I have some issues with my overall heat losses for my heating loads. I know that that's also too high. So I need to reevaluate exactly what it is that I'm designing. This right here was a quick demonstration to show that I need to do something. And I need to do something bad. Because what I'm designing is nowhere near efficient. So So if you get something like this the first time you try it, look at what you can do to improve. And in fact, one of the expectations is to do exactly that. One of your expectations is to change a minimum of 25% of the exterior to an alternate material and see what happens. Does it become better or does it become worse? Learn from it, choose something, and actually implement it within your design. Show us what it is that you're designing. One of the things that we wanted to show is, let's see, where is that? Label all the elements within your building envelope and your overall U values of each building system. Show these in your drawings. Provide wall sections. Please provide wall sections. Showing us what materials you have. Now, do these have to be complete? Do you have to have all the anchors and everything figured out? No. That's not what this class is focusing on. We want to see what are your U values. What is it that you're looking to actually build it out of? Just to see if it's efficient. And when you go through and change 25% of your building envelope, show us what that change is. What did you try to attempt? Look at both options. Come up with a solution that shows, oh, I thought this is a better option versus this one. Why? Is it because it's more efficient? Does it provide better aesthetics? Does it, whatever it is, what are your reasons to make your decision? And again, if both of them are ridiculously high, that's okay. I'm okay with that. I'm not looking for you guys to design the perfect building right out of the box, but at least explain something and learn from it. Okay? Are there any questions on that? All right, so that goes through the overall calculations. I know in the very back we've got E. Also, again, if you guys want to go through it, by all means, go ahead. We do not have time to actually go through it ourselves. Okay? Yes?
We don't know if this thickness rough or anything.
You don't necessarily have to know. That right there, again, is just very, very, very rough. And if you want to use it, by all means, go ahead. If not, if you want to say, it's a standard 2x4 stud with stucco on the outside and gypsum board on the inside, hey, that's great. At least show it. Okay? Any other questions? All right.